In this problem, our vessel is going to carry out an inclining test, and the reason for carrying out the inclining test is to calculate the lightship kg of the vessel. This initial centre of gravity, kg of the vessel, lightship, is a very important value because all calculations involving the GM of the vessel, angle of list, they rely on an accurate initial centre of gravity, kg of the vessel. So it is important that when you're doing your calculations you do have the correct kg, centre of gravity of the vessel. Now in this particular problem we're given our present displacement, our km, and we've got various weights on board. And we're told them all here: ballast, bunkers, water, boiler water, inclining weights. And then we're told that we've got a deck crane which is going to be fitted at a later date. Just before we go on, we'll just talk about the weights. You'll notice that there's bunkers with free surface moments, water with free surface moments. Well, when we come to solving the problem, what we're going to do initially is work out, get our kg at this displacement with these weights on board. What we then have to do is subtract the various weights to get us to our situation where we're lightship. So therefore the bunkers will be off, the water will be off, which means that we would have to subtract the free surface moments. The boiler water, you have to realise here, the boiler water is part of the lightship. So the weight, the kg, and the free surface moments, so that line of values is part of the lightship. So we do not discharge that off the vessel. If the problem says that the boiler water has still to be added into the equation, we would have to add it in. It's already on the vessel, so it just stays on the vessel, is not subtracted. The deck crane that's still ashore must be added into the equation, because at your lightship you will have that crane on board, so that has to be added into the table. So let's look how we originally get, or initially get, our kg in our present situation. We're told our km, but we don't know our kg. Now km is made up of kg and gm, so we're looking for the kg. So if we can get our gm, we can subtract it from the km, and that will give us our kg in our present form. So if we look at the sketch with an inclining experiment, what's going to happen is the weight is going to be shifted across. We're going to have a plumb line and a graduated batten here, and then as the vessel inclines, this plumb line is going to go over at an angle, and we're going to have a deflection. So we're going to have a plumb line length, we're going to be told the deflection, and we've got the length here, as you can see, the deflection here. We've got G to G1, GM here. We know that this angle and this angle have to be the same. So we can find G to G1 because it's the weight times the distance over the displacement. So we can find G to G1. So if we know this one here, AB, we know BC, these two are similar triangles, we know GG1, therefore we can find GM. Once we've got the GM, we can subtract it from the KM, and that gives us our kg. So that's the, if you like, the maths behind the formula. And written here, the formula GM is W times S, which is the weight times the distance that's shifted over the displacement of the vessel, multiplied by the plumb line length over the deflection. So if we look at our problem here, GM, W times S over W times length over deflection, the weight, the plumb line length is 8.24 metres, the inclining weights are shifted 7.3 metres, and the mean horizontal deflection is 0.68 of a metre, and the weights, the inclining weights, are 50 tonne. So we've got 50 times 7.3 over 5330, which is our present displacement, including everything, of course, that weight, and 8.24 over 0.68. Now, Be careful, sometimes you're given a deflection in centimetres. In the formula you must write it as metres. That's why we've got 0.68 there. So we get the GM of 0.8, subtract the km from it, and therefore we've got our fluid, or kg in its present form, 9.95. So there's our displacement, 5530 at 9.95. We now take off the ballast, take off the bunkers, take off the water, free surface moments as well, do nothing about the boiler water, take off the inclining weights, and then introduce the deck crane, because that will be on the vessel when it's light ship. Divide the moments by the weight, and we get a light ship kg of 10.37. So that's how we get our light ship kg. Before we start the experiment, we are initial displacement and km, and the initial displacement includes all these weights. Then how the question is worded, be careful with the boiler water and any weights, cranes, hatch covers that are going to come on at a later date. Use the formula to get the kg at this present situation by getting the GM, and then draw up the table to get the kg. Now why does the kg change? You might think, well, why would it change all the time? Well, various reasons really. We've got the any changes to the ship's structure, internal furnishings, the equipment, the cargo handling gear, sediment and mud in the ballast tanks, residue in the bunker tanks and bilges, debris in our enclosed spaces. Think how heavy paint is when you're carrying tins of paint, accumulation of paint coatings, internal and external surfaces, spares that you've accumulated over time, removal of rust, corrosion from the structure, and any major repairs. So there's lots of different reasons why the kg may change over time. Generally vessels, passenger ships would have theirs checked every 5 years, and other vessels would be if there's a major change to the vessel, or if they feel there may well be a change to the centre of gravity of the vessel.